very much. Now, Stephanie, we've heard lots about your achievements as an adult, but I'd like to start with who you were as a child, because you and I are a similar age, and we grew up when computers were just starting to appear in homes, and I mean, we really are the first generation that grew up with this. So I'm curious about you as a child. Were you always playing with computers, or did that come later?
Yeah, I think I've always enjoyed playing with computers, but to be honest, what fascinates me already then even more is that computers can actually talk to each other at a distance. So for me, I think communication was always central to the picture. Yeah.
That's big thinking back then. And what's your attitude to challenge and difficult tasks? Because back then, if you're thinking about computers communicating, I mean, it must have seemed impossible almost. What's your attitude when a big task or a big challenge comes your way? Yeah. How do you approach it?
I think maybe it's good to say that I enjoy challenges, but I'm not someone who enjoys puzzles because they're an interesting puzzle. I'm a very objective-driven person. And in order to get there, in order to find something out, it may be that indeed then I solve hard tasks to get there, right?
Right. But you can see the end goal. That's what you're focused on. You see the picture. I mean,
to be honest, I think even if I think it's a process, right? If you see an end goal, I think sometimes also along the way you understand the end goal better, right?
Yeah.
I think that's actually even a necessary part of that process, and that also allows you then to get there as time progresses. Yeah.
And before we get on to what a quantum network or a quantum internet might be, did anyone ever tell you this is impossible? That this is just such a crazy idea that it will never work? Or did you think...
Yeah, some people ask that, right? Like, because it's also very difficult to imagine how that might work at all, right? So like, just also because it's quite different. It's different in two ways. Like, so the information that is being transmitted, quantum information, is not something that we experience in our daily life. So the information that we perceive is that you're sitting on this side of the stage, or maybe you're sitting on the other side of the stage, but you're not simultaneously sitting on both sides. So the quantum information we don't see. And that makes it, on the one hand, very abstract to understand how this might work at all. The other aspect is that quantum information also has properties that actually are very good on one hand, because they are responsible for example, giving you these ensuring security. Mm-hmm. But on the other hand, they also mean that transmitting such information works fundamentally differently than transmitting, say, standard or classical information from A to B.
Well, let's get to just a little bit of the very basic physics. As we heard, it's the 100th anniversary of, some would say, of quantum physics. But this word entanglement keeps coming up. And so just explain to us, so everybody's clear, what does it mean, quantum entanglement?
Yeah. Quantum entanglement is a special property that two quantum particles, or two pieces of quantum information, can share. And they can share this entanglement even if they're far apart. And I think entanglement is best described by actually its two properties. One of them being that entanglement is fundamentally unshareable. If I have part of the entanglement and you have the other part of the entanglement, then it's not possible for anybody else to have any share of that entanglement. So this makes entanglement an inbuilt private connection that one can use to solve security-related problems. There's also another cool feature of entanglement, actually, which is that entanglement allows us to coordinate better. So if I measure my entanglement, and you can think of measuring entanglement as asking a question. Mm-hmm. For example, are you red or green, or is it pointing left or right? And if we ask the same question, even though the answer is not determined ahead of time, we will always get the same answer, no matter how far apart we are. And this feature of coordination is responsible for allowing entanglement to be used for problems where coordination is important. like synchronizing clocks, for example, coordinating where requests for videos are sent, and these kind of problems.
And this was a very controversial idea. You know, Albert Einstein, I think, called it spooky action at a distance. You know, he didn't like it. It was very hard that this could be physically possible was a very hard concept for humans to accept.
Yeah.
And yet we can use it. That's the amazing thing, right? This thing that is so far from our own world, you are developing tools that will help us use it. Does that make you feel like a magician? Or is it just all the physics for you?
I don't feel like a magician, no. But I think it's true. Like, I guess you know the famous statement by Isaac Asimov, the science fiction writer, right?
Yeah.
That any sufficiently advanced technology is indistinguishable from magic.
Yes.
So it can sure look like that.
Yeah. So we celebrate you for both being a scientist and for being a magician. Okay, so there's an important point at the core of this discussion, and I know you're keen to make this clear, that we hear a lot about quantum computing, but you're talking about quantum networks, and those are two different things. Explain to me how they are different.
Yeah, they're related, but they're not exactly the same thing. So in the way that one does not need a quantum computer in order to do something useful with a quantum network. In order to have a useful quantum computer, you need very, very many of these quantum bits. So many that you can, be faster than a classical supercomputer. On a network, you only need, say, quantum computers or mini quantum devices that can manipulate only one of these qubits at a time. And that comes from the fact that the power of quantum networks comes from entanglement that cannot be replicated using any classical communication, and it can already exist with one quantum bit at a time. Yeah. So I think quantum networks can be described, or the challenges going forward, in two directions. One of them is distance, meaning how far can the users actually be apart. But the other one is functionality, so what can we actually do with this network? And of course, in further away future, you could also connect quantum computers to such a quantum network to do things that are much more advanced than secure communication. But I want to emphasize that it's not necessary to have a large-scale quantum computer to do something useful. Yeah. Of course, they're also related, because if you have the ability to create a network of quantum computers, you can use that to build a more powerful quantum computers out of the smaller ones. So this idea is not new. This is also how normal supercomputers are built, by connecting together lots of smaller computers.
And do we know anything? You talked about distance being a question, how far apart these entangled particles can be. Do we know the answer to that? Because the quantum theory, as it is written at the moment, or at least what I learned at university, is that once they're entangled, they could be anywhere. Do we know in practice how far apart they can be?
So in principle, like if quantum mechanics describes the world, then they can be arbitrarily far apart. But of course, I think in science one should also always accept the fact that before we did it.
Yes. We need to check that first. Because of course this was part of Einstein's problem with it, that in theory then information could travel faster than the speed of light, and he didn't like that, I guess.
So entanglement does not, I want to emphasize that, allow you to communicate faster than the speed of light. It allows you to coordinate faster than the speed of light, but not to communicate faster than the speed of light. So they are two different things, right? If you can communicate, you can in particular coordinate. But to coordinate, you don't necessarily need to actually communicate.
I will be thinking about that for a while. Okay. So let's get on to the sort of physical, what this looks like in the world. We saw on the video there that there's this very small device that you could carry around. How, in order to do these very clever things, what do you need to build in the real world to actually make it happen?
Yeah. So the box that we just saw is really only one part of the equation here, right? Because what this box, the system that we built allows us to do is to program this without knowing any quantum physics, and to run applications on the network. But to make the network itself, you need very large, complicated devices. You need something where basically the quantum information lives, so a physical device, where indeed kind of the effects of quantum mechanics can be observed. This physically means that we didn't really clearly see it on the video, but there's a chip, a quantum chip. The one that is in Delft is made from diamond material, and in this diamond materials there are quantum bits. So now you need all kinds of things around there to actually perform operations on these quantum bits, because you don't want them to be trapped in this chip, but you want them to, connect to other chips far away, right? So you need lasers and microwave pulse generators. It's complex to build these devices.
And so are we talking, a room or something the size of this hall? Or, is this something you can fit in a normal laboratory, for example?
Yeah, so like our ambition is that this technology does not remain in the lab. So what we just saw is a lab. But we're actually working actively towards to integrate that technology into a normal, it's called rack-mounted, so like what you normally see in a data center, right? Because in the way that you see it in the laboratory, this technology, I mean, it's a lab experiment, but it's not yet technology that can be reliably used over long periods of time. So for us, it's very important actually that this technology does not remain, say, on a table, on a lab, but that it is integrated into racks where they can live in, say, normal conditions in this room, for example.
So what do you think the future looks like on that? Because obviously a big question for society is, will this remain a specialized piece of technology and you have to be a big company or you have to be very rich to use it? Or do you really think that this could be part of everybody's lives? I mean, will it be cheap enough and easy enough to build that this could be in every household? Or, how do you get it to everyone? I guess that's the question I'm asking.
Yeah, I think, to be honest, before we get it to everybody, it will be quite a long journey. But honestly, this is what really drives me. I like the idea that everybody could make use of this technology eventually. And I think there's several things that are important to get there. One of them, of course, is the development of the technology itself, right? It has to work, and eventually it should also become cheaper, right? And I think there, the first users are not people at home. But I think it's extremely important to give access to this technology as early as possible. If you look actually at the conventional internet technology, most of the applications have not been developed by scientists, right? But they've been developed by people who had access to the technology and who used it. I mean, people have proposed to use entanglement even for cheating at online games, which is kind of a creative idea, but you need access to make that happen. Right. So we're also actively pursuing with the Quantum Internet Alliance the creation of an open access infrastructure where you cannot have it at home yet, but at least you can get access to this technology to program it and to write your own ideas.
So there's some central facility where the hardware sits, but then individuals can kind of call in and use something like that, where there's something central that people can access, or is it more?
Yeah, so in the near-term future, indeed, we envision it to consist of a number of different facilities for different use cases that people can access from remote.
So we heard a little bit earlier about the applications of this, the things that a quantum network could allow that do not happen now. What, for you, are the most important things that a quantum network could do that would change our world in a beneficial way?
Yeah. So quantum networks are quite famous for security, so you saw it in the video, right? And I think one of the reasons is because at short distances you can already use that technology, right? But honestly, what I'm most excited about is the range of possible applications. So we are transmitting here a completely new type of information. And to be honest, I'm most excited about, I don't want to call it the other applications, but actually also things that go beyond security or secure
like what? Give us some examples.
We already talked about coordination, so let me start with this. So I like a lot the idea that one can use these correlations or the spooky action as a distance, actually, at Einstein, to already do something useful. To think about how we can distribute videos, for example, more efficiently, so more people can watch videos. I like the idea that one can also use these technologies to do completely different things. Like people have proposed to create entanglement between telescopes to get a better image of the sky. So we know lots of kind of areas of applications.
Right. I can see this is something that, you know, we heard you worked as an ethical hacker for a while, and the job of a hacker, I guess, is to think of try and exploit a system, right? To poke a system and see where you can find ways in things that other people have looked at. And it's maybe a similar mentality, except the other way around, that you've got an idea and now it's a case of pushing it. What can it do? It seems that you really enjoy that challenge.
Yeah. So I know that hacking is indeed also usually considered in the context of security, right? But in a way, let me say on the conceptual level, hacking is actually quite closely related to science. It's to go at the boundary of what is possible, right? To explore without, you know, considerations of what really is the limit. And I would argue actually that hacking is science in a rather pure form.
With a direct application.
Where the goal is to explore, right? What is really ultimately possible. So I think in that sense, what I do maybe in quantum technology is quite similar, right?
So you're just hacking the quantum world, basically.
So I'm interested in going to the limit of what communication technology can accomplish. Yeah.
Brilliant. Well, let's talk a little bit about the European context here. So we have heard that you're director of the European Quantum Internet Alliance. How important has Europe been for you in leading this quantum technology project?
So I would like to emphasize, and it has been said before, that it's, I think, an illusion for any European member state to think they can do it alone. So if you look at the Quantum Internet Alliance, building a network is an extremely complex endeavor. And in fact, the plan that we have for the prototype network, there is no member state where it could be realized by itself.
Right.
So it really has to come all together, on a technological level, but also on a European level, in fact, to make that happen. So on a technological level, I think it's very important, you know, because to create that technology, all different aspects need to come together. But I think to take that step further from technology, like something that has been built for the first time in the lab, to actually usable technology, right? Like a commercially available technology in a new market, that also can only be accomplished at the European scale.
Because it's such a big task. And how, you know, you've worked in America, you've worked in Singapore, I think, you came back to Europe. Why did you choose to come back to Europe?
Well, I am European, this is my home. So I enjoyed seeing other things, and it has been, I think, also enriching to see other places, right? I think if you spend some time in US, you come to appreciate the value of ambition.
Right.
And I think if you spend some time in Asia, you understand that there's limits to what can be achieved by an individual.
Individuals by themselves, So Europe's somewhere happily in the middle. And when it comes to technologies like quantum networks, what's needed in order? I mean, you paint a picture of the future where this could be accessible and it's doing all these jobs. What are the obstacles to reaching that future? What needs to happen in order to have a good future for quantum technologies?
Yeah. So let me maybe start closer to the technology and then maybe go a little bit further to an ecosystem, actually. So if we start at the technological level, so we're building this technology now in the lab, right? That's great. Right. But in order to actually make it usable, we need to go out of the lab. So we have this plan to build this prototype network that is in the lab, but for us it's critically important to deploy outside as soon as possible. To gain also that experience for when the technology goes outside, to engage with early proof of concept use cases with early adopters, to get feedback actually. Yeah. So there's many technological aspects to this, right, that are very important, where we think that beyond the prototype network that we built, like we would like to work really towards a European quantum internet backbone. Yeah. So let's think a little bit about what else is needed, like apart from, say, making the technology and some early adopters use it, and eventually there's commercial pilots, and that's of course great, right?
Right.
But one can think a little bit about, let's suppose that all of this is successful, we deploy the technology in the field, there's early adopter proof of concept, there's even commercial pilots. What then? So how do we scale this technology, meaning that not just on a technological level, but what is needed to actually make many of these, right? Like to go to industrialization. And there, in fact, this cannot be achieved, say, by us in technology itself, right? But I think it really requires a European effort. So I'm talking here about manufacturing capabilities, right, that can ever actually scale this technology. I'm talking here about ecosystem development. If, for example, if you do a very simple extrapolation is how many people are needed at what point in time, in our ambition, you will quickly discover that we don't have enough of them. So, so workforce development is super important. I already mentioned the open access facilities, but a broad ecosystem development is, I think, important, not just to make the technology, but also to retain the technology. So, because, say, if we're successful in deploying it, why should it stay in Europe, right? Right. So first we have to make it in Europe, great, but then we have to consider how does it stay in Europe. And I think for this, like a strong ecosystem that, creates value in being in Europe, and that creates value not just for a few companies that, say, produce quantum network technology, but that do everything that is needed to make network technology successful is very important. And for this reason, we believe, again, in these open access facilities that allow broad development also by people who cannot afford or don't have access to the technology, or companies. Yeah.
Right. Lots of work to do. Okay, so we have heard about an amazing technology. We've heard about what we need to make it happen. What sort of times? I know this is an impossible question, right? But I ask it every year anyway because we're all interested in the answer. How far ahead in the future are we talking? When you said that some of this is available at the moment, but when will this start to be something that a normal business might use, or a normal citizen? How quickly do you think we're going to scale this up?
So I think I already mentioned that there's these two directions, right? So distance and functionality. So I guess it's also been mentioned in the video, if you want to use only secure communication and you're happy with 100 kilometers, you can already buy that now, right? So in that sense, it's a bit more like a gradual development, right? Where distances should become longer. So the prototype network that we envision by 2030 has 500 kilometers. And to do things that are more complex than secure communication. There are some choices in this development going on here, like that I think and for this reason, it's also important to deploy as early as possible and to go to proof of concepts. Ultimately, of course, you can say we'll have very long distances, thousands of kilometers, and we'll have all the functionality that it can deliver. But what is more important after, say, 5 years, I think should be reflected also. Where is the most important near-term market in this technology, right? Is the distance the most important thing, or more functionality?
So we have to choose. And that's partly, it's also, of course, a technological decision, but also it's a society decision. I guess what benefits society? What does society need and want? Okay, so we're almost at the end of our time, but just before we finish this part of the conversation, what's the thing that you're most excited about? Looking forward, you know, you've got some prize money you can do exciting things with, you've got a research group. What's the thing you're most excited about that's coming in the future?
On what time scale?
Fair enough.
Yeah. So, quite honestly, what I would be super excited about, even though it is very far in the future, if there is a first device that allows someone at home to connect to such a network.
Right.
Even just in a trial basis. Yeah.
That's, yes.
So that would be, for me, I think, the most exciting thing.
Well, that is a wonderful thing to look forward to. Stephanie Wehner, thank you so much for talking to me. Thank you. Please, take a seat now.